Well, the wife's computer is on the blink. It's a desktop with a 20-inch Samsung LCD display, 2.5 years old. It's plugged in all the time and just switched on maybe once a day, but it's powered up but not drawing any current from the unit because the screen's off. Anyway, this thing, the screen started going off on its own and it got worse, and now it comes on for a second or two and then goes off and then stays off. As you can see from this power supply, it's supposed to be 14 volts, 2.5 amps, and it's not working. And if I just rest the scope probe on it, here it is, there's just main sum, there's no HF activity. And in fact I did catch it when it did power up, and I could see the 70 odd kilohertz noise from the flux in the transformer. So it's not working, it's dead. And if we just quickly wheel in the old voltmeter, what have we got? Where's the end of that wire gone? Where's it, these wires? There it is. So it's one of these coaxial type connectors with a pin in the middle, 7.2mm I think. And if I just measure it now, see what she's chucking out. .7 volts. So something is happening in there. And I can't really, unless this has got some sort of clever mode where the monitor shuts the power supply down when it's not being used into a standby mode, i.e. it's the monitor causing this. I'm assuming at the moment it is actually the power supply that's gone. So I'm just going to crack this open, have a look inside and just see what we can find out. So I'll get the device out and let's have a bit of fun. Yeah, so before I open this up and take a screwdriver and start beating it up to get it open, I thought I would just do a measurement check. And these two wires here, that's the end of the power connector. There's a piece of wire to make contact with the central pin, and then this goes off to the power meter. There's a constant current load actually, and at the moment, on no load, no current, it's reading 7.5. Actually, it's fluctuating 7.4, 7.5, 7.1, so it's all over the place. And if I put the current up now, we've got 200 milliamps, now we've got 7 volts. 600 milliamps, 7 volts. An amp is 6.9 volts, 1.3 amps, and it drops about just over an amp, it drops right down to 1.2 volts. So it's producing some power, but not at 14 volts. It seems the voltage is all completely wrong. It's very strange actually. So either there's something strange going on, i.e. some advanced function which makes the monitor call for more power, i.e. some communications down one of the power lines, which is very unlikely, or it's just a faulty power supply. So let's open it up and have a look. I would normally just get one of these connectors and run it straight into the monitor from the power supply to make sure the monitor's working, but I don't have that connector in stock at the moment. So I'm going to open this up and let's have a look inside anyway, just to see what we've got, shall we? That is all a bit of a funny angle, but you should get the gist of what's going on. Got one of these Stanley vices. They're quite strong actually, they're steel. And I've got a power supply. Probably best unplug the power to do this. And sometimes these open really easily, other times they're right SOBs actually. But the idea is to get that level with the split line on your power supply and just tighten her up until she starts to complain. Some of them just pop open really easy, some are right difficult ones to crack. Now that's not cracking. Obviously it also depends on the quality of the plastic you've got they're made out of. Some of them are just made out like little more than styrene, or others are ABS, and then good ones which need to withstand being dropped, either polycarbonate ABS mix or pure polycarbonate. Although polycarbonate is tough, it tends to be more brittle when you whack it. So don't do that any tighter, that's really tight. So we're going to have to get some purchase in there and start a crack. Okay, so let's tighten that up. And I shall get, this is quite a good one for the job. Can you see it's got quite a narrow tip, so that should give us a bit of penetration. I've lost my universal tool. I know, I found my universal tool. When you've only got a hammer, everything starts to look like a nail. That's what my dad used to say. And let's give it a whack. Tighten that up. Make sure you've got a good hold on this thing. In the corner. Where's she gone? If you're squeamish, don't watch. Yeah, this is a good quality case actually. Normally they just crack open, but this one is not happy about opening up for me. It's a very good case. You'd expect that from a quality make, wouldn't you? Oh, that sounded like a crack. There we go. So let's see if we can propagate that crack along the top. Talk amongst yourselves. This could get violent. And then give her a little bit of a tweak. Yeah, she's going. So I'm just going to open up. There we are. So look, it's almost intact. You can see that. Look, that edge where it's been ultrasonically welded is only really tacked in several places. It's not really a fantastic joint, but nevertheless it's quite good. So there, she's open. Let's take her apart and have a look and see what's inside. And she is revealed. Okay, let's move this vise out of the way and have a look. Well, look, here she is, out of the case. These are widely available online for about £20, so it appears that there is a roaring second-hand market or a replacement market to get your monitor going, so they're obviously pretty reliable. It strikes me that, if I can find the lid with the part number on, which is temporarily eluding me at the moment, is that anyway it's quite a lot of power for its size. 14 volts at 2.5 watts, which is 2.5, 28, 31, 32 watts or something like that. It's quite a compact little unit, but having said that, it's really nicely made. It's quite nice. It's the soldering is as good as I've ever seen on the base of a power supply, so construction wise it's been made well. There is a slight bow in the board, and if you can see that, that isn't the aberration of the lens, that's actually the board. And sometimes when you've got those kind of bows in the board, if there's any long thin tracks going down the board in the direction of the curve, then you can get sort of fine cracking. But I have had a reasonable look at this, and no cracking at the moment, so it's looking quite good. Don't know if I can zoom in any more than that, can I? Possibly I can. Yeah, there you go, so you can see her. So that's the point. So it's the usual power supply thing. Input socket there goes through you can't see it, but there's a fuse, a rectangular, one of those little rectangular fuses down under there. So it goes in through there, through the fuse. What have we got? We've got a varistor there. That's to absorb transients. That's a very voltage dependent resistor, probably when it goes above 360 volts AC, it'll start conducting and soaking up the transient coming down the mains rather than transmitting it through to the other power supply components that may damage them. There's a negative temperature coefficient resistor there, NTC, to stop inrush current, and then you've got your rectifier over here, your reservoir smoothing capacitor, 420 volts. So slightly higher voltage rating than normal, 82 microfarads, so it's about the right size. Samoa, don't know those. It's a 105 degree one, which is quite good if it's true. Bear in mind this is a Chinese product made in China, so the only thing you can rely on the components really is the label is printed with what it says on the label. So you've got your common mode rejection choke, that's to stop switching noise from here going back out and being radiated by the cable. Conducted immunity, and then we've got a capacitor as well, which is part of this. There's a filter to filter out any switching noise going back down the cable. So there's the current sensing resistor, that will be in series with the primary winding of the transformer, and it's 0.65 0.64 ohms, 0.64 ohms. It's quite high actually. So as the current starts to build in the secondary and it gets to a point where there's enough voltage being generated across this resistor, it's rectified by that diode there and fed back into the management chip on the back, which we'll look at in a minute, to actually limit the current. Okay, so then you've got the heatsink and then the power FET 65E6900. It's not one I recognise, it's probably a Chinese part. And then down here, look, we've got a small reservoir capacitor. See this one? That's the reservoir capacitor for the DC voltage supply to power the unisolated or high side of the power supply. So normally the negative output from the bridge rectifier is called AC 0 volts, and it's referenced to the mains. It'd be at half mains voltage, and this is a DC voltage reservoir capacitor for the drive for the electronics on this side, the low voltage drive. Okay, now what you've got is, I mean, if you look in the other videos, you've seen it, you've got the 300 to 360 volts here, goes through these series of dropping resistors. Can you see there's 4 resistors in series parallel there? And then it goes through a regulator. Did it go through a regulator or a Zener diode? It's difficult to say actually without looking at it. There appears, is that a Zener down there? Let's pull this bit of rubber off. She cried. Let's have a look. Yeah, I'm guessing at the moment that's a Zener diode, so it goes through the regulator, through a diode, through a Zener diode to regulate the voltage, and then stored in this capacitor. And what happens is that these chips, there's a chip on the back here, and I can't find this chip anywhere. It's not one I recognise, because most of the ones that I know that have got the gap in between the pins have the gap between on the 7 and 8 or 6 and 7. So it's not a device, and I can't find any reference to it on here, but it's obviously a switch mode power supply regulator chip that's been copied from a Western one by a Chinese company. And the power supply, the DC volts here, goes through this fairly high impedance chain, so there's not a lot of current available on a sustainable basis from this dropper here. This dropper is simply to charge up this capacitor and put enough charge in it so that when this boots up and starts working, it can work for long enough, powered by the charge from this capacitor, this one here, to get some flux in the transformer to get the thing chooching, and then there's a winding on the transformer that takes over and rectifies and supports that voltage. So, and then going back to this point here, you can see that there's this demarcation, black demarcation line. That's between the unisolated circuitry that's referenced to mains on this side and the output circuitry, low voltage DC, which is obviously connected to whatever's being powered by the power supply. It needs to be isolated from the mains. A couple of surprising things on here. There's your class Y capacitor, which is connected between the DC 0 volts and the AC 0 volts. Okay, so that provides some noise connection to the power supply. So you have got some reference to ground the capacitor, otherwise noise and things would be unbearable on this side. Okay, so it's conducting any noise in the 0 volt rail to ground AC 0 volts to reduce the radiated immunity from this end of the cable where it goes off to the unit being powered. Now down here you can see they've drawn, this is the Opto Isolator, and you can see the Opto Isolator's got a slot in the board, which is good practice because you can get surface tracking, you know, contaminants and moisture build up. You do get tracking across surfaces. So by putting a slot in the board, if there's any leakage across this board, you can see the leakage path is much increased across the surface, because between the Opto Isolator supply connected device connected to the power supply, the AC side of the power supply, and the low voltage DC side of the power supply, you've got to have 2000 volt separation. You've got to be able to survive an insulation test where you provide 2000 volts DC to this side and you don't get any leakage current going through to the main side, obviously, because then the mains could leak back to you, or a transient in the mains could flash across to the secondary side, and give you a belt basically, or destroy your equipment. So that's what the plan is there for that. But what is surprising about it, I don't know if you can see that on there. Can you see those teeth? They're little spikes which we put on our circuit boards to induce a spark. It's called a spark gap. Now this spark gap is absolutely huge because you've got this in the middle of it as well. But it seems odd to have a deliberate spark gap between the primary isolated and non-isolated side of the power supply. So that's a bit strange and really shouldn't be there, I don't think. I've never seen that on another power supply. You can see the spark gaps here again. There probably would jump across. We could put a high voltage power supply on and test that, but at a guess I'd say that would be something like between 2 and 5 kV, that spark gap. Actually that one is very close there, so possibly less. So it'd be interesting to know what spark gap they've put in there. So it's an alternative to providing a spark gap component. You just put a spark gap on the PCB, but of course this is unsolder resisted. There's no coating on, so any moisture would cause that to leak. So if you went from a very moist, warm environment and you went to a very cold environment, i.e. from a very warm, high humidity to a low temperature, you could get condensation and problems across there because they are extremely close. Alright, so anyway, so on the secondary side, up here we've got this photodiode, sorry, a light-emitting diode, and that's not a transistor, that's a photodiode. They've just put that symbol on there, but it's actually a photodiode because there's no base as such. And what happens is there's a chip here which is a voltage reference chip. It's a three-legged voltage reference programmed by resistors, and when one is normally connected to 0 volts, the other one's connected to the supply voltage or a network connected to the supply voltage, and the other one is from the secondary voltage is dropped through resistors to meet a specific reference voltage on here. It's like a precision turn-on transistor at a certain set voltage programmed by resistors. You can see them online. So this is now sort of like giving out 8 or 9 volts, and it's hunting, i.e. varying with time quite a lot. And here is the diode. So what happens is that this will continue to produce power until this diode is turned on, in which case it will turn on, the light will cross the 2000 volts isolation, hit the diode will start to conduct, and as the diode starts to conduct, it shuts down the switching on here to prevent the voltage going any higher. Likewise, and in times of high current demand, the voltage starts to drop, this diode is somewhat turned off, reducing the current in the diode, and this produces more power. So you can see it's a regulation going on, some regulation between the two halves. Now what we've got is a power supply which is basically working. If I just plug this in, I think you've seen enough, haven't you? Yeah. Of course there's the output smoothing capacitors for the DC side, and there's the twin Schottky diode connected to a heatsink, which has got tape on it to stop it shorting out onto the primary side of the power supply. All right. So yeah. So if I just plug this in now, just plug her in. Mind my fingers, everybody. So this is through an isolation transformer. There's no connection to the mains. The only connection to the mains is via the flux in the transformer. Alright, that allows me, if I need to connect my 0 volt probe from my scope onto the 0 volt AC 0 volt line on the high side of the power supply and probe around. If you connect your scope probe to the 0 volts, if your scope is earthed and you don't have an isolation transformer in circuit, which I have over there, then it'll go bang and you'll get half mains voltage right down your scope probe ground lead, and either blow the fuse for this, or possibly blow up the scope or destroy your scope lead. Who knows? If it does go bang, because I've inadvertently I keep some normal unfettered mains connector here, and that's why this one's got white tape on it, because if you plug the wrong one in, it's fireworks. So if I just stuff that in there, alright, so that's live now. So let's just check what we've got on these. I'll just zoom out so you can see a bit more what's going on. The main side is up there, so I'm sort of keeping that away from my body. Make sure you don't touch, usually if you can, keep your hands well clear obviously, and don't make a circuit with your body across your chest, because you will, or could, be seriously injured. Okay, here we are. Here we are. So you can see we've got, let's put that on the 1000. Let's just check we've got voltage on. I think we have, because I heard a spark. Where is the isolation? Isolation on the mine. There's the capacitor, look, with a spark gap between its two leads. And there's 312 volts on there, which is ample to make it run okay. One is not AC 0 volts, the other one is the B plus, or the unswitched power supply voltage. So now if we go across these points here, this is the two output leads here. I'm guessing the black one is negative, but not always. Yeah, so we've got 11 volts. 11 on the volts. If I can make contact, a bit of flux on there. You can see that's varying quite a lot actually. Yeah, you wouldn't really normally call that regulated. That's going all over the place. So 10.5, 10.4. So it's hunting. We call that hunting. It's varying with time and it's not regulated, but it's 10 volts. But there is some power there. There's power there. It's like not as if we connect a load. I've tried the load before, didn't I? Before I undid it, and it was producing an amp, but at about 10 volts instead of the 14 volts as prescribed on the lid. So the primary side is working. There isn't much in the primary side, and there's nothing appears to be overheating. I could just have a look whilst it's running to see whether we've got any hot spots. Usually when you've got something misbehaving, you can often just spot it with a camera. But you can see she's running pretty cool really. There's a little bit of warmth down here, but nothing to speak of. You see that? And if I just turn her over and just see anything on the top that's causing us a bit of cookery going on, frying tonight. No, there's nothing really being dissipated in there. So usually leakage manifests itself, or bad switching, or something wrong with the switching waveform, or leakage in the FET manifests itself as heat quite quickly. So if it could, obviously don't put your finger on it, because you're going to again spoil your day. So to recap, we've got a bit of variation here, haven't we, boys? Yeah, or girls. Yeah, it's going all over the place. So going down to this here diode there, this is the light-emitting diode. So if I just measure the voltage across there on the 2 volt range, we should get about a volt or something like that. Yeah, we've got 1 volt. And you can see it is varying slightly with the variation of the power supply. Alright, so it's hunting down here too. So the input to the optical device coupling across is varying in line with the power supply voltage. Now, because it's varying so much, I don't think it's regulating very well. So if we go to the secondary side, which is the voltage across the photodiode, obviously the photodiode conducts more current. The more LED photons landing on the junction, the more it conducts. It knocks the electrons out the holes and they flow off on their way. So anyway, so we should see a slightly varying voltage across here as well. And can you see it's going crazy actually? So the thing's trying to regulate, but not doing a very good job at all. In fact, it's terrible. Okay, so question is, might be worth just having a quick look on the oscilloscope to see what the flux is doing in the transformer, whether it's intermittently bursting to life or whether it's working okay. I'll just put that next to the there. I should be able to get something on the scope. The scope's booting up at the moment. Come on, scope. There we go. So I'm just going to show you what's going on here. Channel 1. Get the old camera out. This is going to be a bit wobbly because I haven't got my tripod set up, but this will do. Yeah, so there you can see it. You can see that those bursts of activity. That's the power supply chip just topping up the voltage, or starting up and topping up the voltage going into the transformer. So it's inactive and then it starts switching just to top up the voltage in the secondary side. So some demands are being made to that. So that seemed, you know, on the base of it, if you looked at that in isolation, you'd think the thing was working okay, alright? So, but we've got a problem where the voltage on the output of the DC side is just too low. So has the reference gone, or is the power supply not working properly? Is that just starting up, or is it actually running? I'm just going to put a load onto this power supply, then we'll have another look, okay? So let's turn the load on. Alright, so let's just stick a 1 amp load on and see what we get. I'm just trying to get my head around what might be causing this, because normally I would just change that power supply chip and then investigate onwards after that, because the capacitors, it might be a capacitor issue, I'll have to check that in a moment, but the power supply chips are normally quite cheap, and they are in a bad situation in terms of being standing right in the middle of where the transients arrive. A transient juggernaut comes down, and every time they get hit or mistreated or overheated, they get weakened. They heat up and cool down, and the substrate starts to crack. You know, there's all sorts of problems that affect semiconductors, and if they're cheap power semiconductors, they are a liability risk. So I generally just tend to change the semiconductors in power supplies when I've opened them up. But on this one, it's not an option. It's either buy a new power supply or just rule out the chip on this one, because I can't get another chip, because I can't see what the chip is. Well, I know the numbers, but the numbers don't match to anything, and there's nothing online. Right, so anyway, what am I talking about? Load. Right, so we've got a programmable load, which you've seen before. I'm just going to move all my soldering kit out of the way so I can turn the controls. So we're going for constant current. So there she is. Look, we're going for, what are we going for? Constant current. Bom, 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 mode button. Trying to film. So we're on constant current already. The output is off, so it tells you when the output's off and not on, which is not that helpful. And then if we just, because we're on constant current, if I vary this, this will change the set point, right? So let's get a couple of digits in there. 3, 4, 5, 6, and 8, 9. It's not on at the moment, okay. Come on. 1 amp now. Okay, so we're set to 1 amp, alright? What's it doing that for? Constant current 1 amp. Yeah, it doesn't like that. It's, as the output voltage is varying, it's changing its relay inside to switch the, presumably, the configuration and the load depends on some relays in there, switching in and out resistors, I should think, to protect things for a base load. Anyway, so let's just turn around. You can see what the voltage is doing. That's actually measuring the voltage on coming out the power supply, and it's going all over the place. So if I just turn it on and see what happens. Alright, so did you see that? It's on. It's producing 9.3. It's producing about 9 watts, I think. If I just press one of these buttons, I can display watts. Anyway, I'm not going to press that. I'll find it in a minute. So here's your thing. So the actual thing has started regulating. Look. You can see little bursts of activity. I'll just turn the trigger down slightly. Put the trigger on normal. You can see it's pretty jumbled because it's an analog process is dictating a digital switching. If I go to channel 1 on, and then we go coupling, DC bandwidth limit off. Let's put the bandwidth limit on so we can reduce any noise which is affecting the, sorry about this. But there you can see it. I can piddle around. If I have my Tektronix on at the moment, I can trigger on that dead easy. Stop triggering completely. But you can see it's coming in bursts. It's around about 40 kilohertz, I think, is the base frequency. It's quite a low frequency for a power supply. And so it's producing power, okay, so let's just turn that off. So we're producing power and we're not producing anything like the right voltage. Now, if we have a look, just check the DC supply voltage for, let's move that chip out of the way. Let's put my meter back on again, stick it on 20 volts. Let's just have a look on the, do you remember this capacitor here is the one that's providing the DC voltage, DC power to run the electronics which drive the FET on the primary side of the power supply. So that's the DC power supply voltage. Now you can get the idea that that DC side is going all over the place, and it should just not be doing that. Normally that's usually pretty stable. So is that capacitor breaking down, or is it the resistor supply chain? That is supposed to be supported by flux in the transformer whilst the power supply is running, and it looks like there should be enough power to support that voltage. So I'm gonna check this capacitor. I'm going to take this cap out and then just check it, do the measuring on it, and see what we've got. So let's just power this down, just to remove the juice. This is what I use as my 10 ohm resistor to short out the reservoir cap. Otherwise, it's just a nasty bang which I just cannot get used to. So now I use this 300 volts. 10 ohms, and we've got 30 amp peaks for instantaneous current. There you go. I don't know if you caught that. Probably the spark was too quick, but there was a little spark instead of a dramatic bang because of the resistor. Right, so let's put the soldering on. Where's the mother sucker? There she is. Come on, girl. Time for an outing. Right, mother sucker and some flux. Where the flux? There it is. Anybody who doesn't know about the flux, hasn't seen the other videos, this is the flux we use. But it's like very greasy, sticky Vaseline, although I wouldn't recommend you use Vaseline. I wouldn't recommend you use this in the place of Vaseline. It could really flux you up, couldn't it? So let's get a little dab of that stuff. It just makes life go easier. It's not like things go better with Coke. Well, my motto is that thing goes a little bit better with flux. You've got to do some soldering. You might as well enjoy it anyway, as you had. Let's get a bit closer in. Ooh. Right, let's whip this cap out, shall we, and see what's going on. So which two connections is it? What I'm going to do first off is, leaded solder. The unleaded solder has got a higher melting point, and it's just not so much fun to use, as they say. So this solder sucker, this is a Weller one, I think, but the top bit's broken off here. But I got this, I worked in it, when I was 16 I got a job in an aircraft instrumentation refurbishment and service company. And yeah, I was 16, that was in 1983 I got this. I put a new nozzle on it obviously, but the thing still is my preferred, because I find when I'm doing a lot of sucking, my thumb rubs down the end of the guide and it starts getting the nail sore, or things get stuck on your nail. And yeah, so I quite like this. The only trouble is to make sure your inspection light's not too close. So I got one of those magnifiers with the fluorescent tube around it. There was no cover. I went like that and bang, and it broke the tube when I was doing a bit of mother sucking. So here we go. I'm going to suck it off, as it were, for now. Come on, baby, you can do it. Oh, lovely. Beautiful job. Right, we're just going to double check. Before I touch one of these things, I always stop and hesitate just to make sure. It's probably self-preservation based on the times in the past when I've accidentally given myself a shock. There you go. So I think she might come out for us now. Grab hold of it and give it a good tug. That's what I said my wife anyway. Right, hold tight. I'll grab hold of that. There we are. So she's out. And to say it hasn't got the best quality feel about it. No signs of bulging on the top. Well, there's not enough power to make it bulge. 105 degrees, 47 microfarad, 50 volt, LY50V. What do you reckon, boys? Place your bets now. Do you think this is a good one or a bad one? What we can do is just have a really quick look at it with this look. This is the capacitance range on this is buggered. Actually, I think it's because the battery is getting low and it doesn't want to drive the voltage in. But if we just look we'll see if there's any sort of real capacitance there, or whether it's just open circuit, and also we'll see what the leakage current is as well. So first of all, let's just try it on continuity to see if there's a serious leak. I don't think there will be, but you never know. Right, you got that? Can you see it? You can. Okay, so there's no short. There are some 47. Yeah, well, there's a JFP 47. This is the creme de la creme of Panasonic capacitors. Fantastically low ASR. Great caps they are. Great caps. If we go to something like the 200k mode, what do we get? And then stick her back on there, around the right way, so the negative's on my left hand side. So you can see, right, well, you can see the charge as that impedance or the resistance seems to increase. Obviously what's happening is that the very small current that's being delivered by the meter is going into the capacitor and charging up the capacitor voltage. I can demonstrate that now by going back to the voltage mode and just measure the voltage, and she's got 50 millivolts on it so far, so that is ramping up slowly. I go back and just give you another look at that. Right, so it's not measuring the capacitance, it's just, you can say there's some capacitance there, and you can see the speed at which it's counting up. Alright, so we'd expect to see the same from this because they're virtually the same value. Alright, although these have got quite a wide tolerance, sometimes plus 10, minus 20, so the actual value of these things could be within 30% of the stated on the can. And of course, being Chinese, they're nearly always lower. Right. Not that I've got anything against Chinese components, of course, but I'm just fed up of changing them. So let's put that up like that. Just cut that bit off there. See if she'll stand up for us. There we go. Now, provided I can get a contact on this, we can tell whether this cap's any good or not. There you go. I mean, that's counting up at a pretty similar rate, isn't it? Yeah, so it's a pretty similar rate. And if we go down to voltage, let's see how many voltage. What voltage we've got. And it's holding its voltage. Yeah, it just dropped by. It's going down slowly. Let's see what this one's still got in. But I mean, it's nothing alarming has been demonstrated on that cap at the moment. It's sort of very similar to the other one. This one's still holding its voltage at 0.145. So if we just go back and compare that again, if you're bored, then just go and watch something else. Yeah, so it's counting up pretty much the same. So what we can do is go down to a lower range. We're on the 200k range now, and it's getting up to 200k. Now try it on the 2 meg range, and we'll just check the leakage current. Yeah, there's nothing really wrong with that cap that's going to cause us a problem. Should have done it in the first place, but I just thought I'd show you how you do it with a meter if you haven't got a capacitance setting. Right, so let's just try it on this one. Let's give her a go. So there's where's that Panasonic? There she blows. Let's first of all, let's put it on capacitance range. Can you see that? No, you can't. I'm not really looking at the screen, boys. I'm sorry if it's going all over the place. And then we need to set cap on there. Nanofarads, but it will auto range. So get the polarities around the right way. And I'm just connecting her now. Put it up there so you can see. Hold that on there for a bit. Let it stabilise. It'll take us a few seconds to get its reading. Now look at that. Panasonic 49 microfarads 0.0. I know this is pretty accurate because I've got a Wayne Kerr capacitance production measuring machine in the office, and I've checked it against this, and it's not far out. You know, it's a really good, especially for electrolytics. 49 microfarads for the new Panasonic. Let's check the old Chinese one, see what we've got. Oh, it's PET. Hello, PET. PET's just the cover, I think, is the plastic type. Okay, here we go. Going in. We're moving in for the pincer movement. 47.2. Not bad, eh? Not bad. Obviously, the Chinese, when they stole the formula from the Japanese capacitor manufacturers, managed to write it down properly, which is exactly what they did, by the way. Right, so I think we're just going to stuff that one back in and work out which way round it goes. Which way round does it go? Well, it's curious, isn't it? Can you see down in there? They've got a very strange, normally a little plus symbol. What they've got is a big white line. I'm assuming that white line denotes negative, but you can't be sure, can you really? But you can see the cathode, the anode of the diode goes to there, which is that point. So that is positive. That one there is positive. So yeah, that is negative. That white. So let's just straighten her legs slightly. She's a bit spread eagle at the moment. Yeah. Yeah. Just straighten the legs slightly so it makes it easy to get it in the hole, or the holes, because they're quite close together and you can easily, well, sounds a bit fanarish, doesn't it? Right, so if you apply it, if a capacitor's power supply isn't starting up or causing problems, locate that component and check that cap, because it is, if it's got any leakage, you know, like a nominal leakage which wouldn't affect if it was in, say, a DC power supply in the smoothing side, that leakage can prevent the whole thing starting up, because it comes down this 200k 100k divider chain. If you've got 100k leakage on your capacitor, then you've got a lot of the power just being sucked away to 0 volts, right? So she's back in. So the flux in the transformer seems to be lower than it should be, but it should be adequate to provide enough DC power on this capacitor. So have we got just too much power going through the been demanded, or is the bootstrap supply, which is powered by a diode from the primary winding, a separate primary winding on the primary of the transformer on the high voltage side, a diode rectifies the power supply, and then when the thing comes up, starts switching, then you get this DC supply to support the voltage on that capacitor. So windings on your transformer, locate the winding output from the transformer, and you can tell which one it is because it has a higher resistance, a lower resistance than the primary, but I think it's that one. So if we, that diode there switching into there, it says D384, there's one in here, and it would appear that that is actually supplying the power supply to that. So if I go this way, yeah, so if I, on the diode continuity mode, look, if I just meter that diode there, that way around we're reverse biasing it, forward biasing you should get about half a volt. Yeah, and in fact it's just an ordinary silicon planar diode probably, rather than a Schottky, because a Schottky would read 250 millivolts, 200, 250. So the diode's good, the diode's good, the good. There is a winding from the transformer there. Where's the other end of that winding then? That's weird. Oh, there's the other end of it. Yeah, that would make sense, wouldn't it? Because look, we've got this track goes round to the negative of the capacitor, so that's the AC 0 volts line, all this. Check continuity to that point. Yeah, so anyway, look, there it is. So there's one end of the winding, there's the other end of the bootstrap winding, or am I talking rubbish again? That one. Yeah, so the bootstrap winding is between there and there. And then we've got, it says F8833 fuse, that little black component. I don't really, I mean, when you see little blackies like that, I'll just put you on telemacro. Yeah, look, that's that little component in the middle there, that thing, and it says F8833. I wonder what that is. Do you think that's a resistor? It comes from the winding through this component, through this diode. That's the diode there. That's the another diode. That's the positive supply of the capacitor. That's the AC 0 volts. So the rectified juice coming out of there goes through there, through there, through there to this, right? And then powers this capacitor. When that's the bootstrap supply route, if you like. The bootstrap is coming from here, through that, through a diode, and into the stored capacitor. It certainly seems to be short circuit. I wonder what the resistance actually is of that thing. 10 ohm or something? 0.3 ohms. There's another one of these black things, it's called a jumper, look there. Yeah, and that is 0 ohms, so these black things look to be just jumpers, but the question is, why did they put a jumper there? Because there's no track going through the middle of it. Maybe they allowed for a resistor and didn't put one in. That's more likely to be the cause. Yeah, I've just taken a bit of a closer look at this voltage reference circuit, control circuit. We've got 3-pin device in a TO23 case. 0 volts running along there, to there, so that's 0 volts. Is that the supply? Is that the positive supply on that one? Yeah, so you've got positive supply. So this, the voltage output of this kicks in at to control that LED, is set by the resistor divider here, and we've got 10k and 4.7k. So 14.7, so 10 over 14.7 times 14. How does that work out, boys and girls? Should be working on, let's just fire it up and see what voltage we've got on there, shall we? Bit of a laugh. It's going to go out a macro, hold on to your hats. There we are. See what voltage we've got, it's regulating to at the moment. There's no number on that chip, so I'm going to have to guess which one it is and buy an equivalent. So I'm going to have to reverse engineer this to decide which part I need, which is a pain. If they just publish schematic, imagine. Right, across that resistor is the reference voltage. So we've got 2.13 volts, and we should have 3 volts because the output voltage is way too low, look. Right? So that should be at 3 volts. So has this just gone wrong? The voltage reference on there should be, yeah, 14 plus a bit. So it would appear on the face of it that this chip has gone. This little chip down here, this 3-legged jobby, has gone as it's providing current for the photodiode way before the set point. Which it is, isn't it? We've proved that's the case, and it's providing drive for the the LED which stimulates the photodiode way before it reaches its set point. So I'm thinking this has gone a 3-legged voltage reference regulator for that. So I'm going to get another one. I could replace that with any voltage, any one, as long as I change these 2 resistors to maintain the right set point voltage on here from the output. I.e. apply 14 volts on the end of that chain and arrange this so that this is set for the set point of this, and then it should regulate 14. So I'm going to see if I can find one of those. I might not be super straightforward, but I've got tons of power supplies. I mean, literally hundreds of old power supplies in the storeroom, and one of them's bound to have a 3-leg regulator chip which is recognisable, so I can check the voltage and that we can put in there to try it. So should we just try that? I'll just go and locate one and I'll come back to you, but that could well be the cause. Right, so this is what we've got, boys. We've got the transformer here, the secondary transformer. Got a diode there for the rectification and a capacitor for smoothing, and that's your DC 0 volts. And that's essentially, there's other components in there, but that's the V+, that'd be 14 volts going out there, and our 0 volt line coming out there. Now what we have is a shunt voltage regulator, which usually is drawn like this, sort of like a Zener diode. That'll be 0 volts. and this goes through the Opto diode in the Opto Isolator, like that, through usually a resistor to this point here on the diode. So as it starts to conduct, it switches the LED on to turn off the power supply, right? Now what you have on here is a reference voltage, call that VREF, and that VREF is derived from a resistor down here to there and down there. Okay, and on this one that's 47k, and 10k, and there's a cap, and there might also be another resistor in there, but that's essentially the bare bones of her. And when the output voltage starts to rise, the voltage rise here, and this shunt regulator will start conducting in such a way as to regulate this voltage to a fixed voltage, whether it's 2.5 or 3 volts or whatever the voltage for the device is. Okay, so what we've got is what have we got? We've got 10 over 47 plus 10 times 14, and that's what that voltage there should be regulated to, okay, based on the design of the circuit which we managed to glean so far. So if that's at 10 over 57 times 14, it's about 2.3, 2.4. Hold on a minute. Right, okay, yeah, that should be, that equals, as near as damn it, is 2.5456, but it should be 2.5 volts basically. So this is a 3-terminal 2.5 volt shunt voltage regulator, like the TL494 or something like that. So I should be able to just go and swipe one of those out of something in the garage and try it. Even if it's not the same voltage, we want one of the different voltages, we can adjust these resistors to give our 14 volts out. So the next thing I'll do is go and locate one of those, stick it on the board, and then we'll try it out. I'll go rummage in the shed. Right, I managed to find this old power supply. It's an old Bose power supply, but this device here is the same thing. It's a TL431K, and it's a 3-pin, 3-legged shunt voltage regulator, 2.5 volts. But it's not a TO23 package, so the package is slightly larger. The question is, can I fit it in? Let's see what we can do. I'll see if I can just dog wire it in, won't be wrong. Alright, let's just whip the donor off. There she is. It's a different package, but the leads lead themselves, haha, on the pun, to be quite a good, I can bodge it on, put it that way. Not that I'm a bodger, of course. So hot air gun on the old jobby. Let it dwell for a while. Sizzle, sizzle, lots of smoke. Not there yet. What you can do with this situation is just to give her a bit of a prod with the solder iron to get some heat into the other legs. I don't like overheating things too much because it will stress them. And of course on these boards as well, these components are reflow soldered on the base because they've got a mixture of through hole, and now that they're melted, is actually epoxied onto the board. So there's a thing prints a little daub. Can you see that little spot under there? That's the epoxy that this was glued onto the board with. So now we've got the chip off. Right, so we have our chippy. And let's turn that off for the moment. No, we won't. We've got to do the other one, haven't we? So get that out of the way. This goes back to the garage to languish until some other parts are required. Silicon rubber. It's been all. I know that's supposed to be a conformal coating or something. It's just spilled on it in production. Okay, let's give it a bit more heat. I don't want to, if we heat this up too much, this cheap type circuit board will start popping and cracking and delaminating. It's not necessarily that straightforward on these because they are stuck on the board, so I'm going to grab it with some pliers, just give it a bit of a twist. Bit of a twist, see where she'll come off for us or not. There you go. So the old one is off. I think what we need to do is just clean all that silicone off, don't we? Ooh, soldering iron falling everywhere. That's what happens when you get your arm caught in the cable. You get branded. Just under there. Oops, just here. You can see this is a silicone jollop that they've got on it. Why do they do that? A bit of a brush. Kind of hard brushing. No, so you can. There are 3 connections for the SOT23. They're 1, 2, 3. And if I just offer this one up, fortunately this one is round the same way. So you can see, where does that go to? Yeah, the ground goes all the way to there, so I can offset it slightly from its normal centre. And yeah, the leads are right, aren't they? It's just that middle one's going to be a bit of a problem. But that middle lead there is connected to the tab, so I can snip that middle one off and then solder it on, and it should work. He said. What do you reckon, boys? What do you reckon the chances of this fixing it are? I don't want to throw this away, and I want to use it. It's a nice monitor. It's only 2 years old, and my wife is a lovely, lovely girl, and she needs to know that I love her by me repairing her electronic devices when they go wrong. Here we go. So shall we stick that on and see what happens? Do you know what? You've got a much better view of it than I have at the moment, because I can't get close enough because my bonce gets in the way. Right, here we go. Oh, it's a completely boring section. I might just edit that out. I haven't bothered. Right, okay, so we're going to use the soldering iron for this. So I think about there, don't you? I'll melt this down. Let's put some leaded solder on to give us a bit more of a flow, and I've got to break through that silicone rubber coating that's on there as well, which is providing resistance. Is futile. There we go. What a smell. A bit more this way, would you say? Not too far that way, because there is conductors underneath, so I just want the ends of the pins to reach the pads to mitigate the risk of a short circuit onto the 0-volt connection, which is underneath the unit. I'm guessing because it's a shunt regulator, these are capable of, in some cases, dissipating quite a bit of power if they've been used as a regulator rather than a voltage reference. This is really just used as a shunt regulator to regulate the voltage on the power supply. Right, okay, so what does that look like to you? You can probably see it better than me. Well, you can't see it at all, shit. Sorry. There you go. I think that spur there is just a artifact of the manufacturing process. Yes, I'm sure it is. Okay, so you can see she's on. Should we try it? Should we fire her up and see what horrific things happen now? Or nothing at all. Have we made any difference from the component? Let's put the unit back on. Take it out of macro mode. There we go. Right, so the reference voltage of this shunt regulator is the same, so it should work, but will it? So they're going to completely haywire or not work at all. Just going to clean that up with a bit of the old jollop, isopropanol. Right, there we are. Coming a bit closer. Right, so I'm just going to stuff the power in this now. Caution to the wind, and then quickly, if this circuit is not working, then it could drive the actual output voltage quite high, in which case it could blow the output capacitors on this. So the thing is not to linger here, boys, just to assume it's to check its workings. The first thing is to do is just to power up. I'm going to turn it off over there, turn it off on the power meter so I can plug that in. There we go, get it all lined up. Drum roll please. Is this going to work? Okay. Wires on this. I bloody hate wires, don't you? Right, so power on, start. Ready for the bang? Get your mother on speed dial. Right, let's have a quick look, see what we got. Hey, look at that. Look at that, 14 volts. Steady as a rock. We fixed her. We fixed her. So that's what the problem is. It's that little regulator was just cheap and nasty, probably a Chinese one or something. But yeah, 20 quid power supply going in the bin, 2 years old, to now a free component out of the trash bin in the garage has actually resurrected it. So a bit long-winded this video, but it does give you the thought processes. Obviously if I didn't have to stop and explain it, it would have been quite quicker for me, but I hope you found that interesting. If you I'm just going to glue it back in the case obviously now. If you subscribe to using that button down there, I'd appreciate it. But otherwise I hope you found that interesting, and perhaps it might come of use to you at some point.